The pie charts and LOL charts that we've been using to model energy transfer and energy storage in systems are a really good idea, and they can give us a foothold into how models can be used to make predictions and describe how energy is stored and transferred around in systems and out of system boundaries and into system boundaries. And it's really the heart of what scientists and engineers do all the time when they're trying to solve problems by using energy as a modeling tool and a problem-solving tool. However, they don't actually draw those diagrams all the time. They have some shortcuts. And so today what we're going to do is learn another tool for modeling energy storage and transfer that's called symbolic representations. So you might think about these as equations or inequalities. What they do is they substitute what we've seen on, say, an LOL chart with just some symbols. So you can write this down in shorthand and save yourself a lot of drawing. It's a quick way to communicate back and forth with other scientists or engineers what your thoughts are about energy. Plus, they also become a great problem-solving tool because they work just like math equations, because they are math equations once you learn how to put numbers to energy quantities. So here's an idea. This is a chart, LOL chart. You can see that there's some elastic energy at first, and there's some gravitational and some elastic energy later on. And if you look at the comparison between the first and the second, let's call A the start and B the beginning, E at A is less than E at B. That's true. There's nothing wrong about that. It's a good way to symbolically represent what's going on with energy. We could take another look at this, however, and we could make something that's a little bit better. We could be specific about not only which side before or after has more energy, but also how that energy is stored, what storage modes are being employed here. At A, we have elastic, so we could say E elastic comma A, and that's less than the sum total of the gravitational EG at B and the elastic EL at B. So this is an inequality, but it gives us more information than the last one did because it tells us specifically what storage modes are used. Here's the best representation. An equation that specifically tells us storage and transfer that's going on with energy. So here we have E elastic at A plus W, because energy is entering the system through the system boundary through working, and that equals EG at B plus E elastic at B. So this is the kind of symbolic representation that would be ideal for us to be using as a shorthand for an LOL chart. Let's look at another example. Here we have some Echem and some Etherm. Later on we have less Echem and about the same amount of Etherm. So this could be, for example, a car going down the road. This thermostat keeps the temperature at a constant, so Etherm stays the same, but it's burning up some of its fuel. So the energy that's lost through the system is lost through heating. So Etherm at A plus Echem at A minus the heating, so minus Q, equals Etherm at B plus Echem at B. Here's another example. This could be some solar panels heating up during the day and then cooling off at night. So Etherm at A plus Echem at A plus some radiation from the sun minus some heating loss ends up being Echem at B. And I guess there's some Etherm at B that I should have included in this equation as well. So that's an example of how we can use symbolic representations as a shorthand for the LOL charts that we have found is a good tool for modeling energy storage and energy transfer in systems.